theophylline for some of his problems, and theophylline isn't really used that much anymore, but we have tons of data on it. So it's a good thing to use just because we know a lot about it, but the only time it's really used is maybe sometimes in babies that are apneic when they're neonates. The problem is that it has too small a therapeutic range, so it's too dangerous. But it's a good one to just get a basic understanding of how to dose. So, the first example here. So we have a team that wants to start your patient on theophylline. He weighs 100 kilograms with a target CSS average of 12 milligrams per liter. So this is what we're going to be shooting for. So right away we're thinking CSS average is equal to bioavailable dose rate over clearance. So we know that we're going to want to shoot for 12 milligrams per liter. So we look up the population average. The best thing we can do when we're first starting out is look and see what has been a good guess in the past, and that's using population data if we don't already know what this patient does well on. So let's assume we don't know what this patient does well on, so we need to start with population data. So we know the clearance is 0.04 liters per kilogram per hour. So I made this simple, so we multiply this times his weight of 100 kilograms. Those kilograms will cancel, and we can just move that over 2 places, 4 liters per hour. So then we can come in and replace our 4 liters per hour, or our clearance, with 4 liters per hour. And we also know what our CSS average is going to be, right? Our CSS average, what we're targeting, is 12 milligrams per liter, right? We don't need to know volume for our dose rate, but we do need to know bioavailability. So we have a bioavailability of 1, so we can just erase that part, right? So I already know that our dose rate for theophylline is going to be 12 times 4, so it's 848 milligrams per hour is our dose rate of theophylline, isn't it? So I haven't even looked to see what the problem's asking, but I know that we're going to want to give 48 milligrams per hour of this drug. All right, let's go on and actually see what we've asked for. So we're starting a new dosing regimen. Is a loading dose needed? Well, when is a loading dose needed? What is the urgency? What is the half-life? Well, what's the half-life of this drug? We just figured out his clearance is 4 liters per hour, and his volume of distribution, well, let's do the half-life this way, right? His volume of distribution is 0.5 liters per kilogram, so 0.5 times 100 is 50 liters, isn't it? So this is going to times 0.693 will give us a guess of our patient's half-life, won't it? So our patient's half-life is going to be 0.693 times 50 divided by 4. So half-life is 8.66 hours, right? So liters, and we're left with hours. Okay, so 8.66 times 5, do we want to wait 43 hours to get to, which is how long it's going to be, time to steady state, about, we don't know for sure, but it's almost 2 days, right? So do we want to wait 2 days? So we're going to have to wait 2 days. If we start them on that 48 milligrams per hour, it's going to take 2 days to reach steady state, isn't it? Is that okay? Well, it just depends. It depends on how urgent the situation is. It depends on how critically ill the patient is, right? So there's things that come into play here. Is there a pharmacodynamic consideration? Like, is there an active? Is it actually a prodrug where it's dependent upon that active metabolite, or is there maybe like warfarin, a turnover model? Well, let's say we already determined all this, didn't we? I'm skipping ahead. So 866 is going to take 43 hours, so 2 days. So we're going to go ahead and determine a loading dose. So loading dose is very simple. It's just like filling up a beaker. Loading dose. Well, let me tell you a way you can memorize this. When we're looking at a concentration, what is concentration? Isn't it amount over volume? So if we're shooting for a certain concentration, so this is our target concentration. Wouldn't our amount that we have to get put into a particular volume give us our target? So if we're trying to figure out the amount we need to give them, that would be our loading dose, wouldn't it? And if we just rearrange that, it's just volumes times C target, isn't it? So our loading dose is determined by our volume times wherever we're shooting for. Let's check our units to make sure that makes sense. Loading dose is going to be in, let's say, milligrams or an amount. Volume will be in liters or a volume, and our target's going to be in, let's say, milligrams per liter. So milligrams per liter times liters gives us milligrams. Yep, that works out. I always check my units to be sure it all works out. So if that's what we're doing here, our loading dose is going to be equal. What's our target concentration? We said 12 milligrams per liter. And what's our volume of distribution? Well, we already determined it's 50 liters, right? And if we're giving it IV, we don't have to worry about bioavailability. So it's just 50 times 12, isn't it? 50 times 12, we don't really need a calculator for, maybe, is 600 milligrams, isn't it? So our IV is going to be 600 milligrams loading dose of theophylline to get a target concentration of 12 milligrams per liter. So in order to determine our oral, we just need to consider bioavailability, don't we? In order to determine our oral, it's going to be F times our loading dose to equal to our C target times our volume, right? So in order to get our loading dose, we're going to have to divide this all by bioavailability. Our bioavailability for theophylline is 1, so it's going to be the same dose, isn't it? 600 milligrams. Okay. So we've got our loading dose. It's going to be 600 milligrams. We already figured out our maintenance dose, but let's do it again. To figure out a constant infusion is super simple, right? It's just your concentration at steady state is going to be equal to your dose rate in over your clearance. We already figured out that our patient's population guess is going to be 4 liters per hour, and we know that our target concentration that we want is 12 milligrams per liter, right? So our dose rate is going to be 48 milligrams per hour. So that's our constant infusion, isn't it? 48 milligrams per hour. We're going to just infuse it at 48 milligrams per hour. What about our PO dosage regimen? So now we have to worry about bioavailability, and we also aren't going to be giving it as a constant PO administration, right? So We know that, again, CSS average now, because we're not giving it constantly, is going to be bioavailable dose rate over clearance. Clearance, again, is 4 liters per hour. Our target CSS average is 12 milligrams per liter. Our bioavailability, I've made this pretty simple, is 1, isn't it? So again, our dose rate is 48 milligrams per hour, but that isn't the end game, is it? We need to figure out, that's our dose rate, but what's our dose interval? We need to figure out our dose interval. Remember, I told you, unless you know differently, dosing every half-life is not a bad idea. We already determined that half-life is approximated to be 8.66 hours in this person. So why don't we just go with a tau of 8 hours? So we're going to dose this 3 times a day, every 8 hours. So what do we have to do? We have to say, okay, what I usually do is figure out the daily dose. So 48 times 20, 48 times 24 is 1,152 milligrams per day. And then we can divide that into 3 chunks. So it's going to be 384 milligrams per Q8 hours, or 3 times a day. The other thing you can do is just say 48 times 8, which is going to give you the same number, right? So for this one, we're going to recommend 384 milligrams every 8 hours. Now, what if I told you that this drug comes in 50 milligram increments? So you can't give 384 milligrams of this drug. It's very rare you're going to be able to give the exact amount, right? So we have the choice of either giving 350 or 400. Now what we're at, we're actually closer to 400. So let's say if we want to give 400 milligrams Q8 hours, or 350